Well, hello guys. I wanted to make a kind of quick video, kind of from the comments from the last video. This is kind of just a in-between thing. Kind of give you some idea where we're at on some stuff, but also I want to talk a little bit about math again, just a little bit. You know, I showed you in the previous video this formula, or something similar to it. I believe it was this one. F is frequency, which equals 1 over 2 pi times the square root of L and C, L being your coil or inductance and C being the capacitance. Well, I told you that there was a little simpler formula. First of all, right off the bat, the first thing I don't want you getting scared of, or some might get scared of, is 2 pi. It's just a number. Pi is 3.14159, and it goes on and on forever. In fact, someone actually wrote a book that took it out past 1 million places, past the decimal point, just to show that it doesn't repeat. And it doesn't. But for our purposes and for the general purposes of electronics, pi can be rounded down to 3.14. So 2 times that comes out 6.28. So then you don't even have to worry about that. Then it's again times, you know, the square root of LC, and then divide that into 1, or take the reciprocal. Now, this formula, these two are actually with both the inductance and capacitance being at full value of the standard value of inductance, and capacitance, which inductance is measured in henries, capacitance in farads. Alright? Which, you know, for the most part, you're never going to deal with those, so you have to adjust those numbers. Now, there's several ways you can actually adjust the formula. This one here is adjusted so that it's in microhenries and microfarads. Basically, what was done was you take, you divide it out. You put 1 million at the top and divide the 6.28 into 1 million, and you get 159,000, or 159,000, divided by L, the square root of L and C, with L and C being in microhenries and microfarads. The 1 million comes to the fact that now I've went from like henries and farads, and I have moved it to the micro range, which is 1/millionth of a henry and 1/millionth of a farad, which then increases the frequency by 1 million. Take that and divide the 6.28 into it, and you get this number. So you get rid of the 2.28 and you get this number. You can even take it further if you want. You can just play with the numbers, but sometimes a lot of stuff gets in, you know, a little difficult to work with. Numbers become large and everything, so it's best sometimes just to keep the formula in its original form, and I'll show you one way of doing that. One thing I wanted to show out is this is all fine and dandy if you know what your L and C is. You already picked a coil. You already know what the value of it is. You already know what the capacitance value is. Well, then you can figure out what resonant frequency that is. But that's not usually the case. Usually the case, you know what the capacitance is, because you can take, I didn't stage this too well, but you can take, you know, to measure basic capacitance, like a tuning capacitor, you can use something like this, you know, just an LCheapy capacitance meter. That's all. It's fine for measuring, you know, you got like a tuning capacitor that you're going to use in a generator. It's fine for measuring that. So, in case like that, you know, now you know the capacitance, but you know, most people don't have an inductance meter to come up with an inductance. Now you can do some math and everything and wind your own, and I'll show you a formula for doing that. But you still need to find the value of the inductance. So you may know the capacitance, you got a target frequency that you want to deal with, so you got to get from here to here. Well, it works out when you actually arrange the formula, you end up with L, the inductance, being 1 over 39.4 times the frequency squared times your capacitance. Again, capacitance will be in this particular formula in farads. This will be in henries. Now, I can take, I'll show you an easy way of kind of working around some of that, and you can also punch in the calculator easier in just in a minute here. I wanted to go over the basic formula for a coil. Now, this is a generalized formula. It's if you got a coil, you're winding it with so many turns, you know the number of turns, you know everything about it, the diameter of the coil, the thickness of the coil, the length of the coil, and so on, and the number of turns. You can figure out the henries and microhenries, and this one actually is in microhenries, which equals 0.2 diameter of the coil squared. Now that's basically what that means is the diameter, it's not the diameter of the form. I'm not an artist, so bear with me, but here's your coil form, and you have a coil being wrapped around it. Well, that's not really a good way. Here's your coil form here. You got coils going around it. Well, those coils, and this is exaggerated, has a certain diameter. That diameter here is the actual measurement is from the center of that coil wire to the center of the wire. So that's this distance across here is the diameter. So anyway, it's diameter squared times the number of turns, how many number of turns it's on the form, on the coil, divided by 3 times the diameter plus 9 times the length, and it'll be the full length of the coil. Outside edge of coil to outside edge of coil, not from center to center of the wires. Plus 10 times the thickness. Now, if you only got like a single layer, like some of the old radios had in their coils that they use for oscillator and stuff, and antenna coils, and some of their IF coils were just one single layer of wire, then you can get rid of this part. But if you got multi-layers, another set of coils above here and another set above here, and these are wound out like this, then that thickness, and it will be from the outer edge from here to here, that's T. But otherwise, if it's just one single layer, the T goes away and you don't even have to worry about it. This is all in inches, and N's the number of turns, and everything's in inches. Now, what if you know your inductance you want? You got the size of the wire, you got your coil form, you got all that stuff, so you've got an idea what your diameter is going to be, and all that stuff. And say just a single layer coil, I left T out of this, you can figure out the number of turns. So it's just N equals the square root of the entire thing of 3D plus 9L. Okay, 3 times the depth plus 9 times the length divided by 0.2 depths squared, or 0.2 times the depth squared, times that whole thing times the inductance. Take the whole square root of it, it will give you a number of turns that you need to make up your coil. I know that seems like a lot, but they're just numbers. And basically, really what you end up doing here, like in here, you already will have all the information to plug in here. You just need to know what they mean. Now, I said that I would talk about how to deal with some things. You probably heard me mention before that I like scientific notation. What does scientific notation mean? Well, scientific notation basically means is instead of, let's say you got 6 million. Well, you can write 6 million out just like this. Everybody's used to that. Or I can write it out 6 times 10 to the 6. That's scientific notation. It's a shorter way of writing stuff, but it also kind of gives you an easier way of even doing math. And I'll show you in a second what I mean by that. And I'm trying to rush through this, but the thing I wanted to show you was you can work out this to this real easy by a chart I made, and it's a real simple chart. You start with 1. 1 equals 10 to the 0. Now what that means is a 10 raised to 0 power equals 1. No zeros after it, it's just 1. 10 itself is 10 to the first power. 0, 1. 1, 0, 1, 1 here. 100, 2 zeros, equals 10 squared. A 2 here, 2 zeros. 1,000, 3 zeros, 10 to the cube, or 3. 10 to the fourth is 10,000, 4 zeros. 10 to the fifth, 5 here, 5 zeros. 10 to the sixth, a million. 6 zeros, 6 on your number up here. And so on. You have 7 zeros here for 10 million. It's 10 to the 7th. 100 million, 8 zeros, 10 to the 8th. And 1 billion is 10 to the 9th. Be 9 zeros in here. When you got 10 billion, you have 10 zeros, 10 to the 10th. 100 billion, you have 11 zeros, 10 to the 11th. 1 trillion, there would be 12 zeros, 10 to the 12th. Now you can do this the other direction. You've heard of microfarads and nanofarads and picofarads and microfarads, which is nothing but picofarads, and microhenries, and what all that mean. Well, in scientific notation, picofarads is 10 to the minus 12th, nanos 10 to the minus 9th, micros 10 to the minus 6, millifarads would be 10 to the minus 3rd. Here's your number designations. Now the thing I want to point out on this, when you start doing this, you again start out with 1 equals 10 to the 0. Now you got 0.1 equals 10 to the minus 1. There is 1 0. It's over on this side. You always count the zeros with the first 0 to the left of the decimal point. So there'll be 2 zeros here, 10 to the minus 2. 3 zeros here. Remember, 1 0 to the left. You have 0, decimal point, 0, 0. 3 zeros, 10 to the minus 3. 4 zeros, 10 to the minus 4. 5 zeros, 10 to the minus 5. And so on until you get down here to the picofarad, which there'll be 12 zeros. 1 on the left side of the decimal point, another 11 on the other side, gives you 10 to the minus 12. Now why use this? Well, for one thing, it's a simpler, shorter form to ever write it up. The other thing too is, okay, what if I wanted to, well, what if I wanted to take 6 million times 6 million? Okay. Now, pop out a calculator and do it. What if I said you can't use a calculator? What do? Well, I could do something like this. That's the same thing as saying that 6 times 10 to the 6 times 10 to the 6, that I'm multiplying these two numbers together, like that. Wow. So what then, 6 times 6 is 36. Times 10, 10 just follows through to the 12th. And if I want to narrow it down, it's the same thing as 3.6 times 10 to the 13th. But 36 times 10 to the 12 is fine. I'm done. And anybody wants to, it's got a calculator, check it. It is correct. The beauty of using scientific notation is the exponents. When you multiply two numbers together, you just add the exponents. Now the 10s just drop down because that's just our scientific notation. All that's saying is 10 to the 6, I've got 6 zeros. All I got to do is multiply the 6's, get my 36, add the decimal points, or add the exponents, and I'm done. That's all has to be done. So that's why it's used. And if you're doing something like dealing with these negative numbers, it works the same way. You know, you can work through these just the same way because they just add together. That's all you need to know. Except in this case, it'll be subtractions, but it's still an addition problem with a negative number. Now, I'm going to do another video on this because this is kind of important, because one thing that this really picks up on is, and I know there's some of you have troubles with, because I've heard it, capacitors that's just got a number marking on them, like 103, what the heck does that mean? And 102 and everything like that. Well, 103 is just nothing more. If you got a capacitor that says 103, well, you take the 10, add 3 zeros to it in picofarads, 10,000 picofarads. But now, what do? I mean, do you have a 10,000 picofarad sitting in your parts bin? I doubt it. So you got to deal with that and turn that into something else that you might be more familiar with. So I will go over that in another video, which I will do right after this one. I know I promised that I would try to split these up, but this is kind of really, I think, very important. So now, one other thing I wanted to do on this video was show you where we're at. I've started building the generator. I haven't went too far. I just wanted to basically make sure the transformer was operating right. So I just basically built the power supply. Otherwise, I just physically put parts on. We will actually do a lot of this wiring together. I drew up a base start schematic. We're going to be running a 6x4 rectifier, mainly because that way I can have a 6-volt filament. I don't have to have 5-volt extra filament in there. Anyway, all I built is right basically here, other than putting physical, you know, the sockets in place and, you know, stuff like that. But the next stage will be in another video. We'll go ahead and start wiring up the filament wirings to these two tubes. This will be the modulation tube. It's a Triode 6C4. The main RF oscillator will be a 12AT7. One half of it is dual triode. The other half is just a cathode follower. Primary reason for cathode follower is it's a better matching, works better when you're trying to match up to output. It doesn't actually amplify. It's a little less than 1 through, but the match for impedance is better with it. So we'll have an AF output. We'll have the ability to turn on and off the modulation, and there will be a level control to it. Probably about, I don't know, 3 or 4 stages of attenuation on the RF with a fine tuning of that. And it's just 3 bands for all practical purposes, so it's just a real reasonably simple build. But I've just, you know, brought the line cord in, transformers on the other side, primary hooks here. We've got a couple of line filters, 210 microfarad 450 volt filter caps in a Pi network with a 22,000 ohm. This may have to change, not sure until I get all full loads up. And then we just, the rest of just filament windings and running out the rest of it and hooking it up. We, like I said, we'll do a lot of this on video as we go, try to anyway. So anyway, I wanted to show you where we're at on it too, and kind of go over some of this. Hopefully this makes things a little simpler. This is getting really long and I'm sorry about that, but the thing is, when it's a lot easier to use scientific notation, especially when you get into very large or very small numbers. You know, the tuning condenser is on here at the low end, lowest capacitance end of it when it's fully open is like 8 picofarads. You imagine trying to punch that into a calculator, go 0.00000, you might get lost real quick and lose a zero one way or another, a gain to me or a zero or something. So when you can use, you know, 8 picofarads, 8 times 10 to the minus 12, and punch that in the calculator is fine. Well, all scientific calculators will do it. Now they have different ways, different button designations, but I went online real quick and looked at like Walmart and Radio Shack, and you can pick up just a basic scientific calculator. Will do scientific notation if you don't have one already for under 20 bucks, you know, like in the $15 range. So they're not expensive. So, you know, and it makes it a lot easier if you need to do this math, which I'm really messing up, but that way you can leave the formula in the space formula. You can punch in L and C as, you know, micro or nano henries, and capacitance and picofarads and stuff like that. You can use the scientific notation, punch it into the calculator, and get an answer of real-time frequency of what the frequency will be. So anyway, I guess that's where I'm at right now. Again, like I say, I will do another video on this and continue talking about how to deal with some numbers and stuff, and how it's easy just to move from point A to point B on this chart and on this. And again, you can make up your own charts. They're real easy. So anyway, I guess I don't have much anything else at this point. So I don't know what I'm going to call this. Probably Math 2, I guess, or something. So anyway, until the next time, thanks for watching and everything, and your comments, and I'll see you on the next video.